Hi folks, in this video we're going to be working through a case that's designed to demonstrate the process of selecting variables for inclusion in a multiple regression model. As I've mentioned before, this is really not an exact science. When you're selecting variables to include, to not include, to manipulate, to put into a multiple regression model, it's an iterative process. You might be adding some variables in, changing some variables, taking variables out. And so I wanted to run through this case really just kind of give you an idea of the thought process that might go into coming up with a model that is workable and actionable, something that you can actually use. So in this scenario, we are sort of looking at this data from the perspective of a manager of a company who's interested in evaluating sort of the effectiveness of their sales agents in terms of generating sales. So we've got all this data that's meant to demonstrate, meant to represent factors that we might include for analysis in evaluating a sales agent's performance. First off, looking at this data, we've got October sales, that's our dependent variable. And then we've got all these potential predictor variables. And I want to just look at this right now and make sure all these variables pass the smell test, basically. Are they good? Do they make sense conceivably for inclusion in this model? Remember, we don't want to pick independent variables that are just sort of totally out there. So we have highest degree of education earned. Okay, that makes sense. That could be a predictor, a viable predictor for sales success. Number of months experience on the job certainly makes sense. Number of weeks of training they've received, sure. Their score on an aptitude test, great, makes sense. Their personality color. Okay, it looks like we have four. They must have taken a personality test. We have four colors: red, yellow, green, and blue. So yeah, does that make sense? Sure. Their September sales. Okay, this is a time-lagged variable. This is we think maybe their sales in September might have influenced their sales in October. This is maybe a timing trend. Makes sense. Sick vacation days. So for the month of October, how many sick or vacation days did that agent take? Certainly we would expect agents who took less sick time and vacation to do a little bit better because they were on the job more. Although, I could also see it going the other way, which is to say maybe these are sort of long-term negotiations on sales, and really it's not sort of you have to be there every single day to make your sales, but it's certainly a variable that's worth including. And then finally, their base yearly salary. Now, going through this, I think this all makes sense. I think they make sense for inclusion. Not every variable here needs to actually be necessarily a predictor of success in terms of sales, but they might be variables that we want to factor in, meaning we want to control for them and understand their impact on the other variables, which we think maybe are better predictors. So maybe September sales, for instance, is something that we want to include. It's sort of like a pretest. And we want to include it in the model to factor it in, but it's not necessarily a predictor that's all that actionable that we can really use to maybe select better sales agents and things like that. But, basically, this works for us. Now, the first thing I would do is to put these variables into a form that can be used for a multiple regression. We have some variables that are going to need to be created into dummy variables because they don't have numbers associated with them. So that will be one of the first things we'll do. I want to point out at this point that this is actually the second time I've recorded this video. And the first time through, I did every manipulation and ran every regression on the video. And it was a slog. It took a while, and it was boring. I was creating each regression and then formatting the sheet and zooming in so you all could see. And it wasn't good. So this time through, I've done all the formatting, I've done all the manipulations of data and the regressions ahead of time. And so I'm going to try to explain myself, explain the thinking behind each of these changes, and then show you the data without having to run them because I think that'll be faster. So first thing we need to do is to change these variables here into dummy variables. We have 3 levels of education: high school, bachelor's, and master's. That's 3 categories, and therefore we're going to create 2 dummy variables and then leave one of them as not a variable, but it's going to be sort of the default at which we compare the other variables to. So I actually am just going to sort of arbitrarily say high school is going to be the variable we're going to leave out. We're going to have a variable for bachelor's. It's going to be a 0 or a 1 if their highest level of education earned was a bachelor's degree. And another variable for master's degree, and it's going to be a 0 or 1 if a master's degree was the highest level of education earned. Going to do something similar with personality color. We actually have 4 different types of personality colors, so I'm going to leave red out. That's going to be sort of the default, and have yellow, green, and blue all represented by their own dummy variables. And that's going to look something like this. I've actually left in the qualitative variable here, and we have a variable for bachelor's degree and master's degree, each of which has got a 0 or a 1 according to whether that's the highest degree of highest level of education attained. Same thing over here with personality color. Red gets a 0 because that's our default, but green, blue, and yellow all get a 1 if that is their personality color. So with these 20 agents, I've got dummy variables, I've got data I can use. I just need to get rid of highest level of education and personality color, the qualitative variables. And then one more thing, I'm going to show you why I do this later. I'm going to put a line here all the way at the right of the data I'm going to use. And we're going to explain in a moment why we do that. So at this point, I would actually run a regression. I'd go ahead and highlight all this data. I'm going to use data analysis in Excel, but of course you can use whatever program you like. Click data analysis, and I'm not really going to run the regression. I just want to show you the first time through how we're doing this. Find regression, OK. Oh, actually, I have to select the data again. So my input Y range is going to be October sales. That's my dependent variable. My input X range is going to be all this stuff. And I'd go ahead and click labels because my top row is labels. Of course, it's not real data. And I'd click OK. And that would give me this. You're just going to have to trust me on this. This is exactly what it would look like. Not formatted, but this is the exact numbers you would get if I had just run that regression. And let's just take a quick review of this. Okay, we got an R squared that is 0.745. That means 458. That means that that is the amount of the variation in the dependent variable that is accounted for by all of the X variables, the independent variables. And we have an adjusted R squared that is considerably lower. And that tells us that we've got some variables that don't need to be in there, basically that are sort of not contributing anything to our variable, to our predictive power of our model. And so we're going to have to, it's a good bet that we're going to have to take some stuff out. We've also got p-values. I don't care about the p-value for the intercepts, but I care about the p-value for all of the coefficients of my independent variables here. And they're lousy. Remember, a good p-value is going to be something that's like 0.05 or less. That tells us, that with a good degree of confidence, this is significant. This is a significant coefficient, meaning, it's a good predictor for the dependent variable. None of these are really all that close to 0.05. This one's getting there, but what does that mean? Does that mean that we have to give up on this regression and that this is a lousy model, or we have bad data, or there's really nothing that predicts a sales agent's performance? No, I would say no. What I think it is a good sign of is, well, it's a couple things. Number one, remember that we're only dealing with 20 agents. And it's actually pretty hard to get significance with that small of a sample size. When you're dealing with 10,000 data points, if there really is any difference or any predictive power for any of your independent variables in a sample of 10,000, it's going to show up. And it's going to show up as very significant. But with this small of a sample size, we have a high probability of having type 2 error, which is when we fail to reject the null hypothesis, when in fact the alternative hypothesis is true. In which case, since we're dealing with multiple regression, the alternative hypothesis is that these coefficients are actually significant. The other thing, so there's that. But we can get around that. We can work with a small sample size. You can certainly run a regression with 20 data points. What's probably also happening here, and this is sort of borne out by the big difference between R squared and adjusted R squared, we probably have some serious multicollinearity. And to review, multicollinearity is when independent variables are correlated highly with each other. In other words, they have very overlapping predictive power with relation to the dependent variable. And so what we probably need to do, a standard solution with when you have multicollinearity, is to take out some of the overlapping variables, or the variables you suspect are overlapping in terms of their relationship with the dependent variable. So I'm going to do that now. One of the ones that is jumping out off the page at me right here is months experience. It's got a really high p-value, so I would probably remove it anyhow. But months experience is probably going to have a high correlation with weeks trained. Probably is decently correlated with base yearly salary as well, and it's got this high p-value, so I'm going to get rid of it. We're going to remove months experience, and I'm just going to I could do this stepwise, take one variable out or add one variable in, but I'm actually just going to sort of I'm going to be a little bit haphazard here, and I'm going to take out a couple of these personality types as well. Blue and yellow don't seem to be very significant as compared to red. So it doesn't have, there doesn't seem to be much difference between blue, red, and yellow in terms of their predictive power for the sales in October. So I'm going to get rid of all these variables. And my new data is going to look like this. Here's where the line comes in. You don't want to just delete data. At least I don't. You might actually decide to add some of these variables back in. You might find that, maybe they're useful once you've taken out some of the other variables. Or you might just want to, keep them. Keep the data for some reason. I usually do, and I like to see what I've taken out from the original model. So I put them to the right of this line here. As you can see, I've got months experience, blue and yellow all listed here. So let's keep moving with this. Now I've got a new model, and I'm going to run my regression again. And I get this. Notice a couple things. Compared to the first output, the first regression I ran with all the variables, that's this. That's what we're looking at right now. This is the first regression. I had an R-squared of 0.746 and an adjusted R-squared of 0.396. Now, my R-squared has gone down a little bit, but my adjusted R-squared has gone way up. Is that a contradiction? No. R-squared is always going to go up the more variables you have. That's why it's not always as good a predictor of the sort of robustness of your model as compared to adjusted R-squared. Adjusted R-squared takes into account, if you've got variables in there, independent variables that are sort of lousy and aren't adding much. R-squared itself always goes up with more variables added. So we would always expect our R-squared to go down when we remove variables, but that doesn't mean that we shouldn't have done it. Adjusted R-squared has taken a pretty big jump, and so I'm happy about that. Now looking down at my variables, I actually have a p-value that's significant. I highlighted it. Bachelor's degree now seems to have a significant effect, or at least there's a significant relationship between bachelor's degree and the October sales. Other variables are still not significant, so I think there's probably still some multicollinearity going on. I'm going to keep going with the process of cleaning this up. So I'm going to go ahead and remove. Here's a variable I'm not really crazy about. September sales is a little bit weird. I'm not sure how useful it's going to be if, let's say, the significance of September sales with regards to October sales. I mean, we'd sort of expect there to be a trend, right? I mean, that makes sense. I'm not sure what it's adding to the model, and I'm a little bit suspicious that it's messing it up a little bit because it's obviously going to have, well, I just think it might be a little bit superfluous. Let's put it that way. Here's the thing. Like I said, this is not an exact science. You have to have a strong sense, a good sense for sort of how something might be affecting the model, or whether it's useful or not. But it's almost a common sense thinking. I don't see why I need September sales in here, and because I suspect that there's multicollinearity going on with my model, I'm going to take it out and see what happens. So I'm looking at this adjusted R-squared. I'm seeing if I can raise it by removing September sales. So that's what I'm going to do here. In this next, I've moved my September sales. I've cut the column, added it over here. I'm no longer going to run my regression with September sales. I'm just going to, these are my new independent variables here. Everything to the left of the line. See what we get. Okay, looking back, adjusted R squared with September sales in was 0.546. Run the regression again using this data with September sales taken out. It is now 0.566. So a little bit of a jump. I'll take it. Also notice something. Bachelor's degree, the p-value lowered even more, and now we're getting close with base yearly salary. It's almost significant, so I'm slightly encouraged. Also, I think that some of these other variables seem to be edging towards significance, and that's a good thing as far as I'm concerned. I'm going to keep running with this. At this point, it doesn't look like sick vacation days is getting any more significant. It's still at a p-value of 0.411, so I'm going to take that out and as my next step in adjusting this model. So now sick vacation days is out. Let's see what we get in terms of our new model, our new regression, sorry. Okay, adjusted R squared has gone up again. I'm happy about that. Everything is looking good. Bachelor's degree is still significant. An aptitude test is now edging towards significance, as is base yearly salary. It's still hovering around the edge of significance at 95%. So we're making progress. It's incremental, and that's the way this goes with multiple regression models. Now I'm going to do something here that's a little bit interesting. Looking back at our data, going back a step to the data we just ran that regression with, notice something. There are only 3 sales agents with master's degrees. I'd be very surprised if we got any level of significance with only 3 data points. In fact, you'd have to have really very different results for those 3 agents in order to get significance, because now we're dealing with very small sample size. 20 is small enough, but there's only 3 with master's degrees. It's hard to run that in your model. So what I'm going to do is I'm going to combine. I've decided that what I really care about is whether the person has a college education or any kind of post-secondary education, any kind of post-secondary degree. So I'm going to combine this data and make one variable out of bachelor's and master's. You can do that. Nothing that says you can't. Instead of being concerned about bachelor's and master's degrees, I'm just going to take say post-secondary. And so that's going to be our new data point, or our new variable here. I'm removing the variable for bachelor's and master's degree. I'm really just combining them and creating a new variable called post-secondary. And then I'm going to run that in my regression, see what we get. Hey, good things are happening. Look at this. Adjusted R squared went up again, and post-secondary, I'm not surprised that this is a significant variable, as a bachelor's degree was already significant. But now aptitude test is significant, base yearly salary is significant as well. Things are good. At this point, I'm just going to say, I'm going to run with what we've got. I'm going to take out green personality, and I'm going to take out weeks trained. You could argue with me on these points. You could say I should do them one by one, but whatever. This is my video. I'm going to take them both out at once. So that's the new look on my data. All the variables except for post-secondary education, aptitude test, and base yearly salary have been taken out. And when I run my regression now, I have an even higher adjusted R squared. This is probably about as high as I'm going to get it. You can see I'm sort of getting smaller and smaller changes to adjusted R squared. All 3 of these coefficients are significant at alpha of 0.05. And so now I'm going to say, I'm going to stop here. Am I sure that this is the best model with the highest predictive power? I am not sure. Things you could do, there were a couple times where I took out more than one variable at once. I might try adding some of the variables back in. Maybe subsequent to my removing them, I took out the variable that they actually had a whole lot of multicollinearity with. I could add it back in. Maybe they'd be significant now. There's a lot of things you can try. Like I said, this is it's an inexact science. It's not even a science at all. And it's iterative. So I'm not 100% confident that this is the absolute optimum model, but I know this can work. And furthermore, this could actually be useful to me. If now that I have significant, all my variables are significant. By the way, I just want to point out, you could run a variable a model with a variable that is not significant according to its p-value. You would do that if, for instance, you were a researcher and the theory strongly supported inclusion of that variable, and so you're like, look, to match up to the literature and what other people have done, I really want to include this. You're taking it into account. You're not 100% sure it's significant, but you can run a model with a variable is not necessarily that you can't say with certain 95% confidence is significant. You can still run it. But I've got variables here that are all pretty clearly or have a good chance of being significant. And so now I'm going to interpret the coefficients and think about what they mean. This is an interesting result. Looks like if my sales agent actually has a bachelor's or a master's degree, they have lower expectations for sales in a model where I'm taking into account their score on an aptitude test and their base yearly salary. But with those two factors taken into account, on its own, just having a post-secondary education actually is a negative predictor for sales success. In fact, if you have a bachelor's or master's degree, I would expect you to sell almost $2,800 or more than almost $3,000, produce almost $3,000 less in sales as compared to someone with a similar aptitude test and base yearly salary who just has a high school diploma. Now, another caveat here. I made this data up myself. This is not a real company. I'm just sort of throwing things out there. But whatever. I want to demonstrate what these coefficients mean and all that. So here we have aptitude test. This says that for every point on an aptitude test, taking into account someone's education and their base yearly salary, for every point we would expect them to sell on a monthly basis about $620 more. And the base yearly salary, for every dollar earned in base yearly salary, we're getting about a 34-cent return in terms of sales for the month. Aside from just sort of being able to interpret these results, how might I actually use this? Well, as the manager of the sales department, I might look at this data and say, what seems to really be a strong predictor is aptitude test. A strong positive. It has a strong positive relationship with an agent's productivity. So I want to hire people who have high aptitude tests. On the other hand, just education on its own doesn't seem to be doing much for me. In fact, it seems to be a negative. I don't necessarily think that having an advanced degree is a detriment to an agent's productivity, but I'm certainly not going to hire specifically for that. I'm going to take people with high aptitude tests, and I'm not going to pay them any more if they've got a bachelor's degree. I really just want people with good aptitude tests. And there also seems to be a relationship with base yearly salary, though there's a lot of other factors that might play in there. So I'm still not sure that amount of experience, things like that, don't have an effect. Maybe if I took out yearly salary, I'd see things like experience and training, which are all probably very highly correlated, coming into effect and having a relationship. Main thing I might take away here is aptitude test seems like a good predictor. I'm going to keep using that, and I'm going to hire people with a strong aptitude score. Anyhow, that's sort of the whole process here. In this model, we ended up taking out a lot of variables. You might end up doing the exact opposite in a similar situation where you start with just a few variables and you start adding others in and seeing how the others are affected. Really, there's a whole myriad of approaches you might take, but I just wanted to give you sort of an idea of the thinking that might go into building a multiple regression model.